topik begitu. Editing pun tu boleh sir YouTube nak ke
YouTube tu kurang sir.
Meet lagi boleh tu.
Meet lah tu ini itu aku kurang.
Ini YouTube tu fokus tu. Kita meet lagi personally send lagi mana kita like domain name dan lah videos mana. Kalau YouTube tu domain tu pro open platform semua open source ni tu. Itu tu bagus.
अच्छा लो
2 minutes itu lagi lagi.
जब तो रिकॉर्डिंग भी स्टार्ट कर लो 48
ऐसा कि wait थोड़ी मैं बोल बोला
अपन नोए रेडी रखी ना पाहुरी जाए तो रिकॉर्डिंग प्रॉब्लम मीट ला दो
इधर लकुन है क्या बात सेशन ना गेस्ट स्पीकर
कौन हो सोरा सिंगल हो ना ताई जॉइन करना है क्या
Oh, देखो मुझे तो बहुत नहीं लगी डिले लो 20 seconds ना
किधर डिले नहीं 4-5 seconds थे जाए थे ये ना kita buat 7-8 seconds 10 seconds
itu आगे मैं बोल रही थी वाले
ini aja थे ये ना कुआ delay कुंठी हो जाए
oke mana ini itu satu mana boleh
ओए
oke itu cari mana English nama harus nama Devin, go to what was over?
First Laduna.
Shikha आज हम पूरी पृथ्वी को एक मानते हैं। इट इज द ओनली वर्ल्ड वी नो अबाउट। पर इतिहास काफी अलग है। फॉर मोस्ट ऑफ ह्यूमन हिस्ट्री, अर्थ वॉज एन एंटायर गैलेक्सी ऑफ आइसोलेटेड ह्यूमन वर्ल्ड्स। मनुष्य हमेशा से ही एक दूसरे से अलग अपनी ही बस्तियों और सभ्यताओं में रहा है, और तब हम जानते भी नहीं थे कि दुनिया के दूसरे हिस्सों में और भी लोग रहते हैं।
And most famous special
Next because you next you not
कहते हैं कि नागालैंड में लगभग 16 अलग अलग जनजातियां हैं। ये सब कुछ चीजों में एक दूसरे से अलग हैं और ज्यादातर में बिल्कुल एक दूसरे के जैसे, और इसी तरह इनके त्योहार भी हैं। जब पूरे नागालैंड में क्रिसमस की तैयारी चल रही होती है, तब कोहिमा में मनाया जाता है द हॉर्नबिल फेस्टिवल। And I was invited by Camp Zingaros to come and witness this phenomenon. आज से 18 साल पहले someone thought of an event where all the different tribes of Nagaland would come together and celebrate each other's culture and traditions. You see, little things matter in life. जो बीज आज से वर्षों पहले बोया गया था, आज वो भारत के सबसे बड़े क्रॉस कल्चरल इवेंट्स में से एक है, और हर साल ये और भी बड़ा होता जाता है। Now you see tourists and photographers from all parts of the world coming and getting to know a lifestyle which is different, which is very different from their own. और सिर्फ नागालैंड ही नहीं, भारत भर से आर्टिस्ट आकर हॉर्नबिल के सेंट्रल अरीना में परफॉर्म करते हैं। इट इज राइटली ऑफन कॉल्ड एज द फेस्टिवल ऑफ फेस्टिवल्स। हॉर्नबिल आकर मुझे समझ आया कि पिछले कुछ 100 वर्षों में मनुष्य एकजुट हुआ है। हम अलग अलग ज्यादा खुश थे या एक साथ आकर, यह कहना मेरे लिए कठिन है। आई थिंक व्हाट इज एविडेंट इज दैट नेचर एंड एवोल्यूशन हैव वर्कड टू ब्रिंग अस ऑल टुगेदर, एंड इट इज नाउ अप टू अस वेदर और नॉट वी वांट टू कम क्लोजर। Hi guys, this video.
Tik ko.
Alright, Kanado.
Night time mo siya do.
Nagising na. Okay, no more entertainment. Now we wait.
Hello,
Uh,
Hello.
welcome back for the next session, third session of fourth day. So now we are going to start um,
section.
a lecture by Professor Ganapati Panda,
Dati ko parwas. Pin ko doon.
and Professor Panda today will speak
Ah.
about a topic that is binary and real coded genetic algorithm. And already Professor Panda is known to all of you, but still um, I mean, it's a ritual that we should introduce our resource person before he starts his lecture. So let me give you a small
Yes.
introduction about Professor Panda.
Oh,
Professor Panda is currently working as a professor and research advisor at CV Raman Global University, Odisha, Bhubaneswar, India. Professor Panda served as a Deputy Director, Dean Academic Affairs, and Head of School of Electrical Sciences at the Indian Institute of Technology, Bhubaneswar. He was also Dean Administration, Head of Electronics and Communication Engineering at the National Institute of Technology, Rourkela. He was a member of Board of Governors of IIT Bhubaneswar and NIT Rourkela. Also, he served as director of the National Institute of Technology, Jamshedpur. He worked for 48 years in teaching and research in leading technical institutions in India and has a postdoctoral research work at the University of Edinburgh, UK, and PhD from IIT Kharagpur in digital signal processing, and he has guided 42 PhDs in the field of signal processing, communication, artificial intelligence, and machine learning. And also, he has published 380 research papers in various referred journals and conferences with 12,862 citations, and his H index is 53 and I-10 index is 197 as of 12th of August 2023. 8 more PhD students are continuing their PhD work under his active guidance. And he has received many awards. Few of them are Samantha Chandrasekhar Award, Biju Patnaik Award, INAE Outstanding Teacher Award, AICT INAE Distinguished Visitor Professorship Award, and AICT Mark Darshak Lifetime Achievement Award, Ravenshaw University, from Ravenshaw University. And also he is listed under top 20% scientists of the world from the Stanford University in the area of AI and ML. He is a regular reviewer of many international journals and has chaired and delivered keynote addresses at many international conferences in India and abroad. His research interests are in the areas of artificial intelligence, machine learning, digital signal processing, digital communication, and intelligent instrumentation. So, with this, I would like to welcome again Professor Panda to this session and request him to start his deliberation. So, sir, now the floor is yours. Thank you.
Thank you, madam, for giving another opportunity. Right?
Thank you.
I will yeah,
Yes, you are audible, sir. You can continue.
first one will be swarm optimization. Second one will be cat swarm optimization. And after that, the lab section will continue with the quiz, multi-choice quiz. uh, as well as coding as per the sequence. So, like this lecture, I request everybody to carefully listen. I'll make it very, very simple, and you be attentive because your objective test will be done based on my lecture today. Let me first start particle swarm optimization technique. I'll show my slides. Just wait for some time, please.
Caption dia naik ke video deh. Nah, di sini pela do
similar to the actual word na or na convert here.
The slide is visible. Is, is it visible? Is my PPT first slide is visible?
Yes, sir.
Am I
It is
audible?
visible. Yes, it is
Am I?
visible.
This is visible.
Yes, it is visible,
yes,
sir.
This is second slide. Second slide. Is it visible?
Yes, it is visible.
All are able to see this one. Okay. So let me start. Thank you for giving this opportunity. Within this first hour, I will finish two important, simple, and powerful biologically inspired techniques: particle swarm optimization and cat swarm optimization. Okay.
form optimization of particle form.
In particle swarm optimization, it was first started by Everhart and Kennedy in 1995. It is a multidimensional search algorithm. It is the behavior of the birds. Behavior of the birds. I'll give little example. The birds, they get up in the morning, early morning. They have two agendas. They search for food, and if anybody attacks, they protect themselves. The behavior of the bird has been coded in form of an algorithm which is used to solve many difficult problems. We call it cooperative-based learning. It is the birds we also call the particle swarm optimization is a distributed learning. Particles in this case are birds. It started in 1995. The first paper was published. One important thing I'm telling, the particle swarm optimization is considered as a swarm-based optimization. Swarm-based optimization. What is swarm? Swarm means a group of birds. So particle swarm optimization is fundamentally a swarm-based optimization. Particle, we call it a bird. and a group of birds or group of particle, we call it swarm. What happens? They are not jealous to each other. If anybody, any of the bird find a food, then the nearer birds, they get informed. By the nearest bird tell to the nearer bird, the nearer bird tell to the far away bird. So slowly after some time you'll find all birds come to the destination, that is the food source. In our case, please remember the particle position. A particle means bird. A bird has two positions, two information. Remember, a bird has two information. One is the position of the bird, other is the velocity of the bird. The birds fly and moves from one place to another. So it has some velocity. After 1 second, the original position plus the velocity become the new position. Again, let me repeat. The initial position, the bird is there. And after 1 second, it moves certain distance. So the old new position will be the old position plus that velocity. Another thing I told, the population is a set of vector and it's called a swarm. Let me repeat that the particle swarm optimization algorithm is a swarm-based optimization. Each position of the bar, each position of the bar is the solution. And we take a set of solution. Initially, each particular part or particle has a position as well as some velocity. So there is a position vector and there is a velocity vector. The new position will be the old position plus the velocity. Position vector is represented by xit. X represents the position, I represents the ith bar. I means I1, I equal to 1 first bar, I equal to 2 second bar, and so on. T represents the time. Similarly, the velocity vector is represented by VIT. I varies from 1 to number of bars. Suppose there are 100 bars, I varies from 1 to 100. So x1, x2, x3 up to x100 are the position vector. If there are 100 bars, and the corresponding velocity vector is v1, v2, v3 up to v100. When the foot is at certain point, the bar moves from one position to the other. When the bar moves from one position to the other, its personal pace changes. I'll give an example. Suppose a bar is just a human being, a student. A student got in class 1 in mathematics, student got 60 marks. The same boy in class 2 got 50 marks, which is higher. In class 1 or class 2, which mark is higher? His first mark in class 1 is higher. So that is its best. But another part got 70 marks in class 1, but got 80 marks in class 2. So its best is 80, not 70. So each bars update their personal best. Personal best is the best position of the bar until that point. Each bar computes its personal best. Either it take the previous best position or if the new position is good, the new position becomes the personal best. If there are 100 bars and 100 personal best for each bar, the best of the personal best is called the best. So the best of the personal best is called the global best. The best is the best of the personal. If there are 100 bars, there will be 100 personal best. But the best will be one. Sorry, I have developed some cold and fever. So the best of the personal best is called the best. The best at any given time is one bell. Whereas P best, each bar will have its personal best. If there are 100 bars, there will be 100 personal best. So let me repeat. P best is equal to the number of bars, but G best is only one. There are two keys. This equation is very, very important. Initially, you know the position vector, the position of each bar. Position is represented by x. Each bar update their velocity. I means ith bar. V means velocity. T plus 1 means next time. T means present velocity. VIT means present velocity of ith bar. So old velocity maybe in the beginning 0 multiplied by small w. This w timing you assume as 1, but later on I'll explain what is the significance of w. Only thing I can say, in the beginning w is large, that is the bar moves in a larger radius. Slowly the bars when come nearer to the foot soles, the W value correspondingly decreases.
এটা তো watermark নেই। watermark নাই। Length লাগে restriction. The video was something on the video they color channel. Right, open 그럼 이제 인하고 되잖아요. 네. 그래서 타임 시 넣어주는 게 조금 다른데.
टाइम इसी लो सब है ये
한번 더 넣어줘.
एकदम 3 मिनट होगा वी अगला ना एडिट करने ना वी की कारण बुझना ये बाबा एडमिट तो तुम्हारे सो प्रोफेसर विद्यार्थी सब आ रही है अनम्यूट कर लीजिए तब वो
그래서 언니 그리고요.
विद्यार्थी सरकार इसमें मांगा तीन नाम इसमें मांगा
이것도 마시면 이거 제코 텔레비전이야.
Jacob, with them to get the rope. Jacob, where are you? Jacob, come back, Jacob, man, Jacob, God, Jesus.
Jacob, come back, Jacob. Jacob gone. Editing.
गणपति बप्पा मोरया ऐसे
Madam, should I start from the beginning?
Yes, please.
no need to start.
Yes, sir. Now you are audible and also visible your
Okay,
presentation.
I'm starting from this. Okay,
Okay, sir.
this one from the beginning.
No, sir. No. You start from the previous, I mean, the last slide. This
Okay,
one.
this one.
Yes, sir. Yes, this one.
Okay, you see, each particle, each particle means part. Each bar has a position vector and a velocity vector. Position vector is represented by xit. I means ith bar. I equal to 1 first bar, I equal to 2 second bar, I equal to 100 bar. Xi is the position of the ith bar. Position in our case is the solution. If you want to optimize y equal to sin x function, so that either we are maximizing or minimizing, so that sin x is the function, xi is the solution. Once you find the proper value of xi and put into the function, then sin x is the solution, and that is called the fitness function. Whereas VIT is the velocity of the bird. If the bird is not near the food source, then the bird will fly and come near the food source. So every time the velocity of the bird changes. Every time the velocity of each bird changes. I equal to 1 first bird, I equal to 2, second bar, and so on. Now let's see each bar. After every 1 second, their positions are changed. The previous position and the present position of the bar is compared. Whatever position is better, that become your P best. And the best of the P best is called global best. P means personal best. G best means global best. If there are 100 bars, there will be 100 personal best. Whereas if one of best of these 100 personal best will be the global best. In case of maximization, you take the highest of the P best of 100 best. Whereas in minimization, you take the lowest of the 100 best. So G best, remember, is 1, whereas P best is equal to the number of bars. One thing let me tell, that in the next equation I will clarify one very important thing. This VIT plus 1, that is the velocity is updated for each bar, I equal to 1 to 100. W is a timing assumed to be a constant, and it is equal to 1. VIT is the initial velocity plus C1 into rand P dash T minus X1 plus C2 into rand G dash minus X1. That is how the velocity, old velocity VIT, is changed to the new velocity. Now, C1 and C2 are constant. You take some value between 0 to 1. C1, for example, I'll take 0.5 or 0.4. No matter what value you take, but most important part is it should be taken between 0 to 1. Rand is a random number that lies between 0 to 1. Rand, remember, is a random number lies between 0 to 1. P best is the personal best of the ith bar, and G best is the best of the personal. For each bar, P best are different, but for all bars, G best is constant. Xi T represent the position of a ith bar. So in this equation, everything you know. Therefore, you can update the velocity of the each of the bar I equal to 1 to 100. If 100 is the size of the population or number of bars, once you update the velocity from time t to time t plus 1, now you update the position, old position plus the change in velocity will be the new position. This I was explaining in the beginning. So, next one. So this is actually law of parallelogram. To calculate the new position from the old position, you have to get the update the velocity. Once you know the velocity and the vector, you can calculate from this value to this value. So it is basically law of parallelogram of forces. Just see the convergence of PSO. Initially, each bar in this particular space, that is called solution space, there are so many bars, and their position vectors are in this direction. This bar is flying, this bar is flying in this direction. Everybody is flying in random direction. But slowly, after a couple of iterations, you can find each bar, all the bars, are migrated to one position. And that is the most important part. That is the conversion. Birds are searching for food in this place, but by changing their own velocity and updating their GPS, they actually come to one position. And this position of all parts becomes same, and that is the value of the right value of x. Put this value of x into the function, you get the maximum value or the minimum value. Remember, in the update equation, I'll just show the update equation. This term, the second term, this second part of the term, this term actually is called the social intelligence. This term C2 into RAND into G dash minus XIT are called the social intelligence. Remember, this random number lies between 0 to 1. Okay. Another thing I want to tell, the value of W actually varies. In the beginning, this W value usually 0.9, and this W value reduces linearly from 0.9 to 0.4. 0.4. So when it is 0.9, the bar moves in a larger diameter, and slowly the diameter reduces from 0.9 to 0.4. So this is how the particle swarm optimization algorithm works. You start, take number of stars to be 50 or 100, initialize their position vector and their velocity vector. Each bar has two characteristics. Either it is position or velocity. One is position of the bar, other is velocity of the base. Position and velocity. Like this, you go on changing. You initialize the position and velocity of the bar. The velocity of the bar is updated. And after you update the velocity of the bar, the position of the bar is updated. After you update the position of the bar, calculate the new G best. Once you know the G best and P best, you can update the position. From the position, again you calculate personal best and G best. This process continues until all the bar will have the same G best, and that is the solution. That is the fundamental principle of particle swarm optimization. One more thing I want to tell. In this equation, one is the velocity. First important equation of SO is velocity update. The second important is position update. Each bar has to update the velocity, and using the updated velocity, this is the updated velocity, they renew the position. And each bar does that, and wherever they are, they come, migrate, that everybody's xi value from I equal to 1 to 100 becomes same, and that you found that at random position, all parts migrate to the solution, and that is the value of x. Put this value of x into the function, either you get maximum value or the minimum value. So this is one of the variation of the, I told you, that W value changes from 0.9 to 0.4. You can take a fixed value of WK, but if you take this formula and use, and initial W0 is 0.9 and the final one is 0.4, then if this WK is used, then the convergence or getting the solution become faster. And we have used this particle swarm optimization. There are many variations are there, but we have used this particle swarm optimization to solve many important real life problems. And we have published papers. Many of the papers you see, these papers are our research papers. These are all published papers, transaction paper. This is my students have published all the paper, expert system, all the papers have been published. There are more information you can learn by using, we have used in the first one, controlling the noise. We can control the noise, suppress the noise. In this paper, we have used for system identification. This paper we have used, developed new types of particle swarm optimization and improved identification we have done. Yes. I will, in this paper, it is my research papers are all here, clustering. We have used for clustering particle swarm. Here we have used expert system. Particle swarm has been used for suppression of active noise control. This one is also IEEE transaction. All are SCI, high quality paper. In this paper, we have predict stock market. This paper, non-linear active noise control. Last paper, we have used for digital communication considering a conference one. So many works have been done in case of PS. I'll give, yes, I'll give just 30 seconds as a gap. If anybody want to ask some question, I'll clarify at the end. Otherwise, I'll go to the cat swarm optimization. But before I go to the cat swarm optimization, I will give a brief outline of the PSON and where the changes have been made to come to the cat swarm optimization, that is CSO stand for cat swarm optimization. ESO stand for particle swarm optimization. And this thing I will explain to you. Now, remember, the number of P best is equal to number of particles. If there are 100 particles, there will be 100 P best. If there are 100 particles, G best will be always 1. And then I tell you now, I go for the cat swarm optimization. Just wait that show the slides. Okay. Is it the first one is visible? Cat swarm optimization theory and application. Is it visible?
No, sir. The last slide is visible. System identification slide.
Now, visible it has like some optimization theory and application. Is it
Yes, sir.
visible?
Yes, sir, visible.
Now, this particle swarm optimization and cat swarm optimizations are correlated. It is almost same, but remember, cat swarm optimization is much faster and gives accurate results than particle swarm optimization. Before I go to the cat swarm cat swarm optimization, in PSO, as I told you, I have to maximize a function or minimize a function. In case of either of the two, in case of particle swarm optimization, each particle is a bar. There will be a group of bars, and this group of bars is called swarm. Now, this swarm has to be initialized. Each particle or bar has a position value and a velocity value. This you have to assume initial value random. When I talk of random number, it lies between 0 to 1. Between 0 to 1. Random numbers lies between 0 to 1. First thing, there are two key equations. First equation is the update of the velocity of the bar. So, in velocity, initial velocity, assume the personal best and G best in the following. One thing let me tell. In the beginning, what is the position of the bar? That initial position is called the solution. And that initial solution is called the personal best. If there are 100 bars, there will be 100 personal best. But the best of these bars are called G best. How to find G best? Put the position of the bar into the function. Evaluate y1, y2, y3 up to y100. If it is a minimization, take the minimum of y. If it is a maximization, take the highest of the y. And that value is called the G best. So there is only one G best, but there are number of P best. Number of P best equal to number of parts or the size of the population. In case of cat swarm, it was published in 2007. It has two advantages. It is much faster. And second advantage, accuracy or correctness of solution is better in case of cat. Okay. Now, two things you have to learn. Two things you have to learn. One is seeking and tracing. When there is a cat, the cat have two behavior. One is seeking behavior, other is stressing behavior. Let me explain. Please try to concentrate. Seeking means they'll be sitting under a tree, under a cot, or in a corner, or under a chair. Nobody will mark to them. Hidingly they will be sitting most of the time. That is called seeking mode. They'll be observing everywhere in all directions. As soon as some motion or movement or somebody enter or some change occurred or a small insect came, then they become very active. And that trace will run fast. Most of the time they'll be sitting in a place or sleeping, that is called seeking. As soon as a food source or any disturbance, any food came or some animal ran, these people will start running, and that is called tracing mode. Tracing mode. So basically, to solve this problem, we usually assume out of the total parts, total particles, or in this case, total number of cats, 80, if there are 100 cats, 80% of the cat, that is 80, they are in seeking. Any given time, cats, mostly you'll be sitting near a corner, under a tables or a chair, and observe. That is called seeking mode. The remaining 20% of the cat, they will be in the tracing mode. They will be moving from one corner to the other or top to bottom very speedily to hold the food, to catch the food. So two things you learn, seeking mode and tracing mode. Now, these two modes have been explained. The tracing mode is similar to the velocity of rate of the particle swarm optimization. Let me repeat. The tracing mode of the cat, when they move, when they run, is similar to the bird is flying. Therefore, same equation is used. Whereas, in case of seeking mode, I'll explain you. They do not change their position, but what they do, I will just tell you after few minutes. Just have patience. Just please have a look to this particular diagram. Please have a look for 1 minute. Example of the cat swarm optimization. Assume there are 10 cats. How many cats? 10 cats. Each cat is a solution. Example, if y equal to sin x, x is the solution. Putting the value of x in the function and evaluating y is called fitness evaluation. To make you explain, instead of 100 cats, I have assumed that the number of cats are small, 10 cats. Just to explain and make you understand, I am assuming how many cats? 10 cats. 80% of the cat, that is 8 cats, they will be in any given time seeking. The algorithm says 80% of 10, that is 8 cat, will be in the sleeping mode. And remaining two cats will be running. Tracing means running. If there are 10 cats at a place, any given time, two people are moving and 8 cats are sitting. This is the first one. If there will be 100 cats, 80 cats will be sitting somewhere and observing minutely. And 20 cats will be moving very fast to search for food. Now, the second next stage, these eight cats, each of the cat is cloned. Clone means same, just like cloning of tree. They are duplicated 8 times. Each cat duplicated 8 times. That means each cat is made 5 identical copies. So 8 cats become in total 40. How many? 40. First cat, 5. Second cat, 5. Third cat, like that, the eighth cat, 5. So number of left side, number of cats now become 40. What happens to the right side? Right side, there are 10 cats. 2 cats come right side. And these 2 cats will follow, remember, the right side of this 20% of the cat will follow exactly the particle swarm optimization algorithm. Yes, so they will follow. But left side, these 8 into 5, 40, they undergo mutation. Let me repeat. The left side, each one is copied 5 times. 8 cats were there. So 8 into 5 become 40. And these 40 cats will undergo mutation operation. What is mutation? That is, we randomly change the position of the each cat slightly. Suppose the position of a cat is 0.5. By changing, it becomes 0.55. Very small change. Or maybe I reduce something 0.45, 0.48, around 0.5. You can randomly change the position slightly. So every cat has undergone position change, small change, randomly. So 40 cats will have 40 new different positions. Now for each random position, I have to put into the function all their position change because I made mutation means small change, either positive or negative. And to each of these changes, after they are made, each new position of all the 40 cats, after the mutation is over, I put into the function. I got x1 to x40 solution, x1 to x40, put into the function. Let us say y equal to sin x. I got 40 values of y. How many values? 40 values. And instead of keeping 40, I keep only 8. How I'll keep the best 8? The first cat has undergone 5 copies. First cat has produced 5 identical copies. And these 5 I made mutation, so the magnitude is changed. After the change in magnitude, these values are put into the function. Suppose out of these five mutated values, the second gives the best performance. The next cat has undergone again five copies, and this each one made five. So there are 40. There will be 40 such values. So each five values, I choose the best one. So out of eight group, I choose only eight, one from each group, because each group contains five. From each five, I choose the best one. So I choose only eight after mutation. So five were made 40. From 40, I choose the best eight. Now, this best eight, I got the solution from the left side, which is the process of, this is the process of seeking. Right side, only two cats were there, 20%. And I update the position like particle swarm optimization. First update the velocity, then update the position, and I got two updated cat. This side I got eight updated cat. Both are mixed. So 8 plus 2 again becomes 10 new cat. This process is repeated. Again this 8 cat, sorry 10 cat. I made 8 into 2. Again I made 8 into 2. This side will undergo PSO operation and this side will undergo normal cupping, and from each set of cupping choose the best one and keep the 8 here. Made from 8 to 40 and 40 to 8. This 8 plus this side 2 mixed together become 10. And this process is repeated many times. And you'll find and you'll be astonished that these cats, their initial positions were different for all 100, sorry, all 10 cats. But after a couple of iterations, following this principle of cat swarm optimization, all cats migrate to one position, and that position is called, that position we call it the solution. Everybody's cat started with different position, but because of these two operations, the right side operation is called tracing. Tracing follows particle swarm optimization, whereas seeking follows copying, followed by mutation and the selection of the best one. This process continues. And in case of your cat swarm optimization, we must know that cat CSO stand for cat swarm optimization. And CSO is based on the behavior of the cat. The cat has two behavior, seeking mode and tracing mode. And another important part, that is a swarm-based optimization. CSO and PSO both are swarm-based. Swarm means a set of birds, a set of birds or a set of cat. They are called swarm. This particular principle we have used to sort direct. First day I was telling, if this is a physical system, this is an adaptive system, but this system we have built by particle swarm, cat swarm, and we have also done inverse modeling in communication channel. But this model was developed using particle swarm and cat swarm. and we solve problem. There is very less time to explain on this. What we found, you can see the convergence is faster. The TSO converges very late, but cat swarm converges faster. See, convergence, we tested with real life example. It doesn't convert. Error is high, but the error mean square error diminishes very fast and accurately in case of cat swarm. You see, it is very slow. It is doesn't convert here, but CSO converts much faster. This is our published paper. With these types of system, we work both for direct and inverse modeling. Basically, cat swarm optimization is a swarm-based optimization. Its behavior is much fast seeking mode, tracing mode, and by following this seeking mode, which is different from TSO, right side is TSO, 80% of the part undergoes seeking mode, 20% of the part, or cat, they undergo tracing mode. By combining or this hybrid quality makes the accuracy better and makes the convergence faster. And these are some of my students have used for cognitive review, who have used some of these were expert system. So a lot of paper we have done on cat swab. So this is what about the Billy algorithm, which is much better than the yes. This is two things I was to cover today, and this I covered. But again, I'm giving a summary that both are swarm-based optimized. Second, I told, in case of TSO, there is velocity update, position update. Velocity update is done fast, then you update the position. And the velocity update second part is nothing but the social intelligence. That is called social intelligence. The random number used lies between 0 to 1. And TSO, there is a controlling parameter W that actually controls how fast a bird can come and catch the food. W is initially, the W value is initially large and slowly its value become small. The next one, TSO, if there are 100 parts, there will be 100 personal best, but one best. GA is another types of algorithm which I'll be teaching on Monday. So that is genetic algorithm. Genetic. It is the first algorithm, and this particular algorithm is an evolutionary algorithm. Whereas the previous two algorithms are swarm-based optimization. Swarm. But this is evolutionary. And the genetic algorithm is of two types, binary type and real coded type. In case of genetic algorithm, we use selection, crossover, and mutation. First one is the process is selection, then you make crossover, and then mutation. I'll teach on Monday. But whereas the PSO takes first one is velocity update, then V-based update, G-based update, then position update. And that flows. And GA-based algorithm, they are based on natural selection, natural selection, then crossover, then mutation. These are certain fundamental things you need to know. And in case of cat swarm optimization, one of the behavior is called seeking mode, where they will be observing in a standstill position. Other is tracing mode. The tracing mode of cat swarm optimization is exactly same as the particle swarm optimization. And remember, cat swarm optimization is much faster than BSONGA and gives very good result. So thank you for giving this opportunity to cover these algorithms. And my student, my colleague come students, they will explain how Madam will decide, Sujata Madam will decide. First, they have to make the which multi-objective test, or they will go for the coding, showing the results. The code explain all the three codes, and basically they will show the results. So after this, as Madam says, after a little gap, we'll go for the second part. Thank you.
Thank you, sir. Thank you for the presentation and nicely explained the technique. And we are also ready for the next session, next hands-on session. Sir, whatever you like, you feel like explaining uh, first, you can go for that. Because anyway, we are here to learn, and everybody will they can use Python code, because sir will explain through Python code. And during the session you can also interrupt if you encounter any type of problem. Otherwise, you can practice parallelly. If you want to practice, you want to do it, you can also do that. Otherwise, just try to learn while the team will explain, and after that you can practice and also clarify your doubts, uh, talking to Professor Panda. His mail ID will be available with you. We will share it, and you can contact him. Better, you can, if you contact his student, the Dr. Adyasa. Today she will explain the code. So because Sar is not well, and in spite of his bad health condition, he insists me to take the classes, and he didn't even I mean, tell me that he is not well. Otherwise, I could have arranged some explained you very nicely. And these two algorithms are very useful. Till today, many people, I mean many researchers, they are applying in different type of problems. So try to learn from him, and it's an opportunity that you got the chance to learn from Professor Panda. He is a pioneer of this particular field and very renowned, and not only as a academician, as a teacher, but as a researcher. And he has produced a lot of students, lot of PhD scholars, and his scholars are they are well placed and working in different organizations in a very high post. So I hope all of you will enjoy his session, his hands-on session, and will cooperate uh, with Dr. Atyasa. And I would like to invite Ausang. Awesome to introduce Dr. Adyasa. Sir is, no need any introduction. Panda sir, already all of you know him. So now over to Awesome. Awesome, please introduce Dr. Adyasa, and after that we will start the session. Thank you.
Thank you, ma'am. Okay, I welcome everyone in this fourth session, day 4 of FTB. Now, in this session, the topic is implementation of PSO CSO GA for optimization of standard benchmark functioning of Python. Along with Professor Panda, Dr. Adyasa Rath will be joining us. She is a researcher working under Professor Panda and has currently received her PhD. Dr. Rath will be demonstrating the implementation of some meta-heuristic algorithm in this seminar. So now I would like to give the time to our speaker. Please, sir, take your time.
Thank you. Thank you, Awesome. Dr. Adyasa, did you join?
Madam Namaskar, I am Adyasha Rath. Hello.
Namaskar, Adyasa. So welcome to
Hi.
our FDP last final session. Yes, you can start.
Okay, actually, me and my friend, we are both are doing. So I'm showing you the code now.
Admit code is একবার
Okay, let me tell you with Dr. Adyasa, Saurav,
Yes,
one
ma'am.
of the PhD
Adyasa,
scholar of
sure, ma'am.
Panda sir, will explain the code. Both of them will handle this session along with sir. Thank you.
Thank you, madam. Give me some little bit of time.
Okay.
Okay, so for every day we have to send separate things for you. Yeah.
একটা স্টার্ট করেছে 5 তো বুঝি যায়নি 5 পার হয়ে যায় পুরো বুঝিলো না হলে আসছে আর না কোনবা জয়েন করি না
We can do through one
Very
to
good.
yeah.
They just
So just can send that.
no no to video to
Not the problem.
এটা প্লে করি দেয় তো তো ভাই না এটা কনফিউজ করে দেবো মুঝে the session একটা স্টার্ট হয়েছে আর ওই
FORE F1KI dari image level
Image of the problem.
ini dalam bawah ini jangan like you have to instruct what to do and
Set on them as well. Like not near everything all of it.
কিছু করে দেয় ও না না এটা
So it is like to delete what it says,
ওই তুমি দেখে তুমি বলে
FP saja Here we send it out.
Oh, itu sistem admin ada semua. Itu pun boleh itu jangan. Sistem admin account dah.
Oh,
Delete kode itu nanti
itu
delete kode.
ना itu content generation itu banyak apa ना
Pura delete kode.
खाली नॉर्मल होता है ये भी जैसे डालते ना फ्रॉम सब लाइक होता है प्रोफेसर अंदर प्रोफाइल ना फ्रॉम कॉमन फ्रॉम प्रोफाइल अपलोड करो हमारा ऑनलाइन ने पाजो रेज्यूमे है ना
तो itu delete kode ini kan. Baik.
और itu आगे डालो
Itu saya tanya. Itu tentang bahwa itu testing berita. Connection to solar tanki उसको भी नहीं
Then the virtual is yeah, but then
बुलाई जाएगा तो 3 बजे लास्ट में सर
just start the show huge
अगर अलग कोई करी
हेलो
हेलो इसमें अब तो नेटवर्क प्लीज ना
network stuff
स्टार्ट करिवे भी ना टिके अपेक्षा करिवो
Profile 54 is in my account. मैं recently delete किया तो वापस लॉगिन मतलब account recently delete किया
फेसबुक पे जीमेल का ना लगे तो इन पे ऑन क्या
no मैं recently delete किया
ठीक है सर ठीक है
ना लगे तो जोड़ने
ओके सर ओके
इसी का नाम है
नाम कोई काम ना
ऑप्शन
break regularly close to now depending on the
फिर अच्छा अध्यक्ष मैं कॉल करना फैसला करेगा 그럼 좀 따라 personal 전화만 전화
yeah more
सबकी प्रोग्राम में कभी ट्रांसफर
सर वीडियो डाउनलोड कीजिए
सब making oh
आधा 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 होगा ना 30 minutes
oh 30 minutes
30 minutes पावर होगा ना तो अगला वीडियो कटे ना 40 ना ना इसको
so
तो इधर हमारा कोशिश से ऐसा लिखा हुआ है ना वो बनी la carte del CEO de la carte
pen của tadi saya cerita drawer deh.
ini itu Panda gitu ya. Itu online upload online.
Oh itu drawer.
Panda gitu lah gua. Panda. Mau print for the time. Devan, itu kamu gitu lah.
नहीं तभी नहीं हो
फिर
दोनों दोनों
मतलब
की फॉरवर्ड दो
मैंने
वीडियो दो नहीं मुझे तो पूरा
कुछ है
तभी नहीं हो
Rohit, you are not audible.
Friday दिन
Hello, hello.
Yes, Rohit.
Am I
Now,
audible, ma'am?
yes, audible.
My screen is laptop screen is visible to you, ma'am.
Not yet. You are presenting, but we are not able to see anything in the screen.
Okay, ma'am. Wait.
Any shortcut keys हो कोई क्यों नहीं है मुझ छाड़ी मुझे वो फुल होगा मुझे कंपाइल नहीं है Kibuye. Muy bueno, la forma sai na plus.
Rohit, you unmute yourself.
Muy tagara compare bodu alak chalo editor. Free.
Hello,
Yes.
ma'am. My screen is visible to you. Laptop screen.
it also same size.
Yes, now it is visible. And your voice is also audible.
Okay, thank you, ma'am. Good evening, all of you. My name is Rohit Sharma. I'm the doctor student under the guidance of Professor Ganapati Panda, and along with me, ma'am. My screen is there, na, ma'am?
No.
Hold on.
Yes. Your
Sorry for
screen is visible.
Okay, ma'am. Thank you, ma'am. Good afternoon, all of you. My name is Rohit Sharma, and I'm the doctoral student under Professor Ganapati Panda, and along with me, Adyasha Rath is there. So both of we are going to continue this session, hands-on session. So in this session, we are going to present a population-based technique. The code for population-based technique. These codes are written in Python programming language. So we are going to use three population technique. One is two techniques are based on. Ma'am, audible? Hello.
Yes, you are audible.
Okay, ma'am.
Please go.
We are going to demonstrate three techniques, population-based technique. These three techniques are particle swarm optimization, and then we will discuss CSO, that is cat swarm optimization, and then we will discuss genetic algorithm. Okay, so particle in population based technique we have three kind of we generally divide the population based technique into three types. Uh, one is based on swarm based technique, then population based swarm based technique. The second one is physics based techniques, and the third is evolutionary based techniques. So the particle swarm optimization comes under swarm based technique. The swarm based techniques generally mimic the behavior of animals and birds. So first of all, I'm showing the codes on particle swarm optimization. Uh, every population weight technique, in every population weight technique, we have to in the starting we have to uh, initialize the population. Then we have to write the main code for the that algorithm. So in the Python we have to import necessary libraries. So for particle swarm optimization we are using these are the libraries which we are going to use. It is a very basic code, and for this
आपने लिखा अनुश्री न्यूजीलैंड पोस्ट कार्ड
uh, am I audible? Hello.
Yes, yes, you are audible.
Okay, okay, ma'am. So, first of all, we are going to import libraries. We are importing random libraries, then math, copy, and system libraries. These libraries necessary for the successful operation of the particle swarm optimization in Python. Uh, in our evaluation we are going to optimize two main optimization function or cost functions. The cost function generally divided into two types. One is unimodal function and second is multimodal function. The unimodal functions are those function. uh, there are a lot of functions, but we generally consider in here two functions. One is unimodal and second one is multimodal. The sphere function which we are showing in here, it is the unimodal function. Unimodal function are those functions which have same one local and minima and same global minima, global minima or global optimum values. Look at this function. This is the two dimensions representation of sphere function. Here we write the code for this function. Okay, so look at here. This is a sphere function. We just plotted it in two dimension space. X1 and x2 are the two dimensions. So look at its shape. It has only one local minima and it has very smooth shape. It has same local minima as well as same global minima. So these type of function are easy to optimize. So we are considering both kind of problems. So this is the sphere function. The equation or the function uh, the function is shown like this. uh, Here the fx is equal to I is equal to 1 to d, where d represent the dimension of the function x I square. It is nothing but summation of the square dimensions input variable. So it is a continuous and convex function, as well as it has d dimension, and we are going to optimize this function. Its general value input range varies from minus 5.12 to 5.12, but we can change its values. So global minima is at the origin. When we are going to optimize this function, we will find out that we should have the values at the origin. These values should be 0 0, uh, goes from whatever dimension you are taking out. So the second the Python codes are in here for the sphere function. So this is very a simple function defined. In this we have input position xi, whatever be the input position, it will be given in here. So we are going to calculate the value. It is nothing but fitness will be summation of fitness value over uh, summation of the x square over different dimension. I is equal to in the range of length of the position. right? So we will discuss it is in detail later. So this is the second function is a Rastrian function. So Rastrian function is, as I already told, that it is a multimodal function. Multimodal function, look at its landscape. The function itself has a lots of local minima, and it has only single global minima at value fx is equal to 10d. Okay. So Rastrian function, the detail are mentioned in here. Similarly, similar to sphere function, we can write the code for the code for the Rastrian function. This section represents the Rastrian function, in which we are providing the input position, and then we are going to calculate its fitness value. The fitness value will be we calculate the summation part will be the summation part is calculated in this for loop, and in the return we will add the 10 sorry we add the 10d. Okay, this will be the 10d, 10 into length of the position. Length of the position means we are going to add the the size of the dimension. Okay, so after that the here we now we have what is now we have defined our cost function, which we are going to be evaluated. So next part is, as I already know that it is a population weight technique. So we require different number of particles. So for the particle purpose, I am going to define a class, that is the particle class. Okay, so every particle in particle swarm optimization, they have each individual particle has its own position related to it. Its velocity is there. Then with its personal best is there, personal best position is there. We have to confine its position and the velocity within a specified range. Okay, then we have to calculate the fitness value, and after that we have this is the this is the individual personal best for each for the for each particle, and as well as this is the fitness value calculated for uh, for each particle. Mean right now we are only creating a class of particle. So we are initializing using init function. So we are giving it a fitness function, then a dimension, the problem space size. Right now in this example I'm going to consider 10 dimensional problem. Then input variable or the particle positions value should be in a specific range. So x is defined, maximum x is also defined. Seed is used in here to reproduce the code again. So we have initialized the random generator in here. Okay, so for uh, in here so in here we we started you we create a position input using for loop for I in the range of dimension. Dimension means here we are considering dimension value is equal to 10. So it will be it will be a it will be a list of 10 having length 10. Similarly, velocity will be having a range of 0 to dimension size. Means it has the same size as equal to position. After that, we initialize the best position for the particle. In the initialized state, every value has a each velocity position, and best value has value equal to 0. So in so after initializing, we have initializing all the values. We are creating a random position value whose range is in maximum and minimum. Okay. After that, we similarly created we initializing the value of velocity in the maximum and minimum range. Right. Then we evaluated using this function fitness function. We evaluate the fitness of the particle. The function has input that is equal to position, and we calculated the fitness. So for the particle, we calculate the best position and best fitness value. After initializing the particle, we started our main PSO function. So PSO has different hyperparameters which are shown in here. First of all is inertia weight. Wait for a minute. So this is the mathematical model for the PSO, right? So PSO has two main terms. One is position, operated position, and the second one is the operated velocity. So we have different hyperparameters in the PSO. W is there. It is a weighting parameter, also called inertia is there. So this part is called a cognitive component. It is related to. I will show in detail in later. And third one is the social component. So we have different parameters which are going to be decided. So we have W, that is the weight. uh, Initially we have given the value 0.7 to 9, but it can be varied. It generally it is varied from 0.95 to 0.20. In the most of the in the particle swarm optimization algorithm, its value is varied along with the iteration size. So and the C1 is the cognitive component of the particle. It is related to the personal best, means every particle, how much will be the impact of its oven, means its personal best. It will decide by C1. C2 is a C2 uh, is there for giving the impact of global best. After that, we have initialized a random number generator. Now, and here fitness uh, is the is the function to be evaluated. Then maximum iterations and total number of iteration for which the algorithm to be run, and is the population size, the number of particles in each iteration. Then dimension, as I already told, that dimension means the size of the problem landscape. Minimum x is the minimum value that can be used in the variable input variable. Similarly, maximum is the maximum value. So as I already told that we created a particle class. I create a particle class for an individual particle. Now we have to create it for the whole population. For that purpose, we use a for loop. For I in the range of n, n is the number of population in the whole loop, in the whole population. It is the population size. So we will create a different particles in the swarm variable, right? In the swarm list, it is a list. Okay. After that, we are we are we are we are initializing for I in the range of dimension. We are initializing the best position for. Okay. Sorry for break. uh, Here we now we have initialized the total swarm, mean total population. After that, we initialize a global best position, means there should be a global best and multiple personal best. So we already initialized the personal best along with different particles. Now we are going to initialize a, a global best position. The global best position has the same dimension as dimension of the problem space. So for I in the range of dimension, we initialize the global best, right? So similarly, since it is a minimization problem, so we have to choose a maximum value of the initial best cost, so that during the comparison it will be suitable for the for updation of the global best. So we define using this code, this line of code, we are going to provide a maximum floating point number for the best, for the global best. N-
Ele both party because copy dili part mo yung pinili na.
So after that, we are going to check each the particle for I in the range of n, means for I in the range of population. We are going to check the fitness value of each particle and compare it with the global best fitness value. So if the global fitness value is great, if we found any particle which has less than the global best value, we are going to update the update the global best. This is the global best value, and this is a global best position. We use the copy function because in here, because we are going to change the value of position uh, as with the
Eight, nine, four, seven, four, four.
with the swan position, right? So this loop is going to compare each particle fitness value with the global fitness value. If any of the particle value fitness value is less than the global fitness value, then we are going to change the global fitness value with that value. And similarly, we are going to change the position of the particle global best, for which the we obtain the global best using with that position, that swarm position. So this is just initialization loop till now. Now we are going to start the main loop of the PSO. So iteration, we initialize the iteration with 0. Then we decide the convergence criteria. If the iteration is less than maximum iteration, we continue the loop while loop, otherwise the loop will be terminated. So these are the equation we written for showing the string, showing the message on the screen after every 10 iterations. Here we shown that iteration modulo 10 equal to 0, mean after every 10 iteration we are going to show the results, right? So this is now we are going to update the, as I already told you that this is the main mathematical equation for the particle sum optimization. So we have to calculate the velocity first, and then after calculating the velocity, this velocity is used to update the position of the particle in the next iteration. So for this purpose, we have to change the particle position of each particle. We have to calculate the velocity for each particle. For that purpose, we started a for loop for I in the range of n. N is the population, and the for k is in the range of dimension. Means if we have a 10-dimensional vector, then we are a 10-dimensional vector. Then we have to change the each each value in that vector using this loop. And using this loop, we are using this loop for each particle. Means we have different vector, we have a matrix, we have matrix. That matrix contains in the row wise it has a population, and in the column side it has the dimensions. So we are starting one loop in the row side and other loop in the column side. So for as I Here we have two parameters R1 and R2. These are random parameters. So we initialize two parameters R1 and R2 random parameters. So as I already told that for the particle I, we are changing the velocity. K we are changing the we are calculating the velocity. Sorry, we are calculating the velocity. So this is a very simple loop. It is not very much tough. So we are calculating this one. After calculating the velocity using these codes, then we are going to limit the velocity or clip it so that it is not going out of the landscape. If the velocity is very high, then our algorithm will jump in zigzag, means there will be no convergence in the solution. Very less. It is not possible to converge very fast. So we are, and the solution will be uh, out of the feasible space. So here we clip if so we this use this loop. If velocity is less than this one, minimum value, then we are clipping it using a threshold value that is equal to minimum value of the input variable. Similarly, we for if the maximum velocity is going out of the limit out of the range, then we are going to change this velocity with the maximum threshold value, that is maximum x value. So this using this loop, we are going to calculate the velocity, operated velocity. This code is related with this equation. So wait for this. So here again I'm emphasis on this portion here. Okay. This is the next iteration. This is the velocity for the next iteration. Its value is given by the given by the current value of the velocity multiplied by the inertia weight. Then this portion is related to the individual component, or it is also called cognitive component, and this component is connected to the related to the global best and this is called social behavior, means how different particles are going to interact with each others. Similar. So after calculating the velocity, operated velocity for the next iteration, we are going to add this velocity with the current position. So using this for loop, we are going to update the position for the next iteration. Then we are going to calculate the fitness value of the new positions, which we calculated from this equation. Now we are going to find out we are going to update the personal best as well as global best. If the fitness if the fitness is if the fitness value is less than the personal best, then we are going to update the personal best. Similarly, we are going to change the personal best position. If a particular population or a particular swarm has a fitness value less than the personal best fitness value, then we are going to change the position of the personal best position using the position of that particular swarm. Right? So, hello.
Yes.
Yes,
No,
sir.
you just carry on. Yes, you carry on.
Okay. So after that, here we are we have here we have here we have find out the personal best. in this loop we are going to update the global best fitness and global best position. So for that what we have done, we uh, compare the best fitness of each population, each particle with the global best. If the fitness is less than the global best fitness, we are going to change the global best fitness value, as well as we are going to change the swarm position with that swarm global best position with that swarm position. After that, so this one iteration is going to be complete. What we have done, we have calculated the new velocity. We limit the velocity within a particular limit. Then what we have done, we update the position. After that, we calculate the fitness value. Then we calculated the okay. We find out the personal best for each particle. Then we find out the global best using these equations. Now our one iteration is going to complete. Then when we increase the fitness, then we increase the iteration number. So and in return, we since it is a since it is a function. So in return, we return a best one position. So in this way, one iteration is going to be completed, and this loop is continue till maximum number of iteration are going to be completed. So as I already told that we are going to evaluate two functions. We are going to evaluate two functions. One is called Rastrin function, that is a multimodal function, and other is the sphere function. So first of all, I'm going to evaluate Rastrin function. For that purpose, I'm going to comment this one.
Where is it been reported because of the I believe writing into this week before most
So this is
day 21 but day 26 तक छुट्टी हो गई थी स्कूल में when तो quarter education आज एक करना no idea no
this now I'm running the code for this wait for a minute please. Okay, now I'm running code for this function, and this function has a global optima at, as I already told, that it is at the origin, but it is not actually at the origin, it is at the 10D, means 10 is into number of dimension we are going to use. Although this function can be modified in some literature, that this term is avoided. This term is not in there. Modified Rastrin function. For that function, the value is should be 0. Right now, its value should be 100. The best fitness value should be 100. So, what is happening? Wait for a minute. So right now we can change it by deleting this one. Okay. So here ITE are the iteration numbers, and this is the fitness value. Now look at this. The fitness value now it should be 0. Since I modified the code, if I delete this term, Since in modified Artesian function, this term is avoided. This term is deleted. So at that time, our solution should be converged to the origin. So okay. So number of iterations. So this is a 10-dimensional problem. I use dimensions equal to 10, and the fitness function is Rastrian fitness function.
Are you mining
This is
pi or
nothing,
not?
just we are printing
Pi.
our reference point that the output should be at the zero.
Third is here.
So here is the hyperparameter parameters. The number of particles. Here we are using 500. Let us suppose we are going to decrease the value of this number of particles. So number of particles are 10. Suppose, and number of iteration I'm going to decrease. Suppose they are 100. So now we are running, and this is running very fast. Okay, so now the fitness value we are getting 46.886%. Now you can find out that what is the impact of increasing the number of iterations. So if I'm going to increase the number of iterations, so I increase the number of iterations. So still, since the number of particles are very less, these are 10, and the maximum iteration are high, but still we are not going to achieve the optimum value, that is 0. Here we are getting the value that is 30, which is very much high from our expected value. So let us increase the value 20. One thing also, okay, 20. So now we are getting a 15 value, that is equal to 15, which is also which is again a large value, which we are expecting that should be near 0 or equal to 0. So again I'm going to increase the value of number of particles. It is now again decreasing, then we are again increasing 100. Now it is decreasing, still need improvement, so we can increase 200. Let's
How
see.
much is transferable to our wallet? Which is depend question na. Muy lagi 700 plus will be.
I think there's about 3.5 to 5% of.
Look at it. We increase the number of particles. In the last run, we got 0.99 value, but still we increase the number of particle. In the ideal case, our fitness value should be decreased, but it is not decreasing since these algorithms are stochastic in nature. They have randomness. So how many number of times you are going to run, you will get a different result. So again, if I run this code again,
44 bytes. No, out of 778 migrated which is there. So this much I can withdraw once they start. But again, मुझे से तान ना.
What are the sufficiency?
Let's go with 300.
Hash reason and some other new cat.
दूसरा हम लोग माथा खाओ मन नहीं नहीं पाए तो नहीं कुछ हो ना.
Dogecoin itu core bagian main.
Let's change hyperparameter. Initial weight I'm going to change 0.95.
The Bitcoin gimana dia proses ini?
I think it's 13.
It is okay. Look at the different hyperparameter are going to show different results. Now the fitness value is going to increase. So it is happening because these algorithms need a fine tuning of different hyperparameters, and with practice you can find out that what will be the value. In most cases, right now I didn't write the code. I write the code, but I forget somewhere. Wrote a code for a variable value of w. In that case, the value of this is going to be changed as a number of iterations are going to progress. So right now, let's go for 0.45.
Draw from the every human hours mind blow every 4 hours. 4 hours. Hey, you do it but in the body.
It is
Every problem is UIC
the point
message কথা বলে তো আমি UIC না
3 5 and 2
মই ইজানো না ঘুরে ঘুরে না পারি না
point
KYC বিদিন না 1 week নাকি মধ্যে না 1 week নাকি মধ্যে
नहीं नहीं जब ओपन तो ओपन है ना
ना सभी वाले मतलब बहुत say you have only 7 days or something to upload your KYC or else আপনি যদি বলবে KYC যদি দিস হলো
মই এক দিন দে সব করে দিছি
let's increase number of particles. What happened? Let's see. No, look. Now look at this. Now we are getting a global minima value. In the real case scenario, in the practical case, as since the function is already defined, we are commenting that this is a global optima. Since we are known to we are already known with the function and its equation. But in the real life cases, we can't comment that the value we obtain is the best value or the global. So it may be changing with the different hyperparameter. In the practical situation, we didn't have the knowledge of global best value already. So, but in here, as we already know that the value is minimum at the origin. Origin means all the dimensions has zero value. Right? So look at here what is happening. Our solution is going to be converged at the iteration 790 iteration. So by increasing the number of particles and choosing a best possible combination, we got a global optimum value for the raster function. Similarly, this function is a little bit difficult because it is a multimodal function and it has number of different a number of local minima and single global minima. So, but here in case of sphere function, we have
2 lakh users. No, 2 like 10 lakh users. Everyone does 12 hours every day. Don't go get 6 lakh users.
Now let's run for this one.
Every day, 12 for 7 days.
Okay. Now we are going to run this for. We are going to run it for sphere function. So look at it. This function is a very smooth function, and this function is going to be converged very fast. Even we need a look at here. So it is converged at the 70th iteration. So even we didn't require a large number of particles. What is the disadvantage of selecting a large maximum iteration value and number of particles is that if we selected a number of large values, then more number of calculation has to be performed. So there is a trade-off between high accuracy in optimized algorithm as well as number of calculation. And then let's decrease the value of number of particles. Look at it. Look at this. This function is so it is not that much complex than like a Rastrian function. Look at it. With 10 particles, it is going to get a global best value at only 120 iteration. So even we can decrease iteration to 200. And this solution will be available. No, with 200. Okay. Look at the value is somewhat differ from. Right now we didn't get a global optima. Look at here. The fitness is 0.0006. That's why the value is not at the origin. Again, let's try for some. Oh, it is not going to converge. I guess the fitness will be very less. So this is the whole about the particle swarm optimization. So I'm open for the questions. Any question? I hope I represented well. So any question related to particle swarm optimization, you can ask the questions. Then I will shift to next algorithm. Any
Yeah,
third?
one question. Yes, yes, you ask. Dr. Bharat Kumar, you can ask your question.
Sir, I have a question that do we get global optimal solution with PSO?
Actually, as I already told that we in the standard problem, like which is already defined, we can comment. It is a very good question. We can comment that we got a global value, optimum value. But in practical life, practical problem, we can't comment on it. We can say that suboptimal or they are optimal or they are best among all, among the rest. We can say.
Okay, sir, thank you.
Thank
Sir,
you.
one more
So
thing,
his
like
question okay, let me just, he asked what are the constraints we have to tune to achieve global optimal solution in PSO? What are the
Oh,
constraints to tune?
ma'am, I didn't get your question. Actually, this problem is a unconstrained optimization problem, which I
Yes,
told
that
you.
is right. That is
It
the answer. Yeah.
Yeah, it is not a constraint problem. It is a very simple problem. I choose because otherwise I have the whole theory is very large. So it is just a starting point. It's basic, very basic codes, and there it is possible we can add different kind of constraint in there. We add if our solution is going out of the a particular constraint, then we can add the penalty on that. So different possible ways are there to address the constraints. But right now it is not. It is an unconstrained optimization problem. No constraint is there. But in here, what we have done, we only limit the input landscape, means search space, by providing where it is minimum x, that is the input variable value, minimum x and maximum x.
Another
That's
session.
it, ma'am. Hope I'm able to address your question, ma'am.
Yes, yes, it is. Any more question? Okay, now you move on to the next one.
Okay. So, uh, hello,
Yes.
ma'am. Only 30-second break I need. Just I mean, water
Okay,
drinking
sure,
water.
sure, sure.
Okay,
You
ma'am,
can.
please, na? Okay.
Yes.
Except like so that.
Anthony, can you play some music?
Oh, sure.
Hello, Anthony.
Yes, ma'am. Yes, yes, I can.
Uh, Just for refreshment, can you play a good music?
Even when things seems to be moving according to our plan, there may be something else at play, guiding us. When you are being led in a direction that completely strays from your vision, how do you choose to respond? As a result of the global pandemic, traveling, festival feasting, even walking outdoors has become difficult. Life has become confined in many ways unimaginable. Following proper SOPs laid out and carrying only my camera and my willpower, I somehow wanted to illustrate this special day. I went out to the fields of different Aonaga villages, discovering a newfound love and sense of pride that I belong to the land of festivals. Allow me to share with you with all of my heart Jangram Festival. In every part of the world, culture and tradition has been passed on from generation to generation. And even with the vast modernization of our society, we are constantly reminded of our proud roots. The same applies to the Onagas, and I've personally been able to experience of how
Rohit, you
beautiful my
want
culture is.
to continue?
Sangamong, when
You want
roughly
to start
translated,
now?
is associated to thank.
Hello? Yes, ma'am.
You want to start now?
Yes, ma'am. Yes, ma'am.
Shall we stop?
Yes, ma'am. Yes, ma'am.
Okay.
So, this is as I already. Hello, I'm audible.
Yes, you are. You are audible.
Yes, ma'am. So, ma'am, hello, I'm audible, na, ma'am? Okay.
Yes.
So, as I already told that population-based optimization algorithm are generally defined into three sections. One is okay. What will but I already told that the population-based algorithm are categorized into three sections. One is population. One is swarm-based techniques. Second is physics-based algorithms, and third one is uh, that is evolutionary-based technique. So the two techniques we are going to discuss, that is CSO and PSO. They are swarm-based technique, and the third one is that is genetic algorithm. That is the evolutionary stage techniques. I guess I have to go with the genetic algorithm first, and then I will, since one swarm-based technique is covered, then I will go to GA. Then I guess I have to go to CSO. So, wait. As a in the last code run, we used PSO. The same problem I'm going to address with genetic algorithm. The genetic algorithm. Yes, ma'am.
Excuse me, Rohit, you start your presentation. We are not
Okay.
able to see anything.
अच्छा, ma'am, audible.
Yeah,
आवाज आ
you
रही
are
है?
audible. Yeah.
Okay, ma'am. Resume. Okay, ma'am. Now it is. Hold on. Yes, miss. Now it is visible, ma'am.
Yes, it is.
Okay. So this is a code for a genetic algorithm, which is very much popular, just like a particle swarm optimization. So in genetic algorithm, it is a evolution-based algorithm. In this algorithm, uh, evolutionary algorithm are generally governed by law of natural evolution, in which initial random population is generated. So in genetic algorithm, we have two code files. One is app.py file.
ऑप्शन ट्रेडिंग भेजिए स्टॉक्स मतलब खाली दूंगा ना तो ऑप्शन ट्रेडिंग मतलब एक तो
One is app.py file and second is the GA file, right? So in the first stage, we are going to import our library necessary libraries. So we are importing NumPy just like a normal libraries, and PyPlot for as a PLT for plotting purpose. We are using a special kind of library in here, that is BiPStruct library. From BiPStruct library, we are using a structure module. We are using structure module in here for the purpose that it is similar to other languages, just like in C and other C++. The structure is used to store different kind of variables at a same place. So that's why we are using a structure here. We're using a structure, the whole code will be very easy to read as well as to run. We can we can make changes in the code very easily. So in the fifth line, we are importing GA. Here it is a GA. I will explain everything in the GA. Let's complete our importing section. Then last in math, it is similar to all. They are not just nothing but they are the importing necessary libraries. Then we defined different cost functions. Then we defined different cost functions. Similar in here, I also added a 10 into the dimension of the search space. So it is we can also change it if we needed. Otherwise, the global optima will be at the 10 into the number of dimensions or number of the input variables. So here we are going to define the problems. First of all, we define the fitness functions. Then we are going to define define the two structure. The first structure is related to problem, and the second one is related to the second structure is related to the parameter related to the genetic algorithm. Okay, so for the problem structure, we have four variables stored in it. One is a cost function. Cost function is any function which we are going to evaluate. Right now it is a Rastrian function. We can later change it from Rastrian to sphere function. So it is very much simple. We have to put the name, we have to change the name, and automatically the result is evaluated for that function. So here in the last section, in the last code, we run the input for 10 dimension. Here we can also change it to the 10 dimension, but we have to just put in here 10, and the variable minimum and variable maxima is also going to change. So if we want to change, we can change it. So but right now let's go it with 5 dimensions, and this is the input variable value, or you can say that this is a gene or the range of chromosome value which can take place in genetic algorithm. Chromosome population is made up of chromosomes, and each chromosome is made up of genes. So it is a range of genes. Okay, so right now it is a chromosome range. We can define maximum variable range and minimum variable range. Similarly, for we again create a different structure, and using this structure we define maximum number of iterations. We define number of populations, but particularly the size of total number of chromosomes those are going to participate, or the total number of parents. You can also call parents in the parents. They are going to participate in the in the optimization process. Similarly, beta is there. This beta is not, I'm not going to use, but it is generally used for the selection purpose. Selection purpose means we have different technique for selection. Right now I'm going to use the random selection techniques, but there are different techniques. It's like a tournament selection technique. We have we have a roulette wheel selection techniques. So it is used in a roulette wheel technique for the purpose of calculating probability probability which is used in roulette wheel selection technique. So right now it is I'm not going to use it, but I will run the code, but I will not define right now. We are going only we are going to only focus on we are going to only focus on random selection techniques. So this okay, so this is the total number of population. We are population is just like number of particles in the case of PSO. Here, the number of particle, or you can say the number of population is going to take participation is 50. There is PC. As I already in the genetic algorithm, what is going to happen? There are the different stages. Just like selection is the one, as I told. Then after selection, there is a crossover, and then mutation is there. So the PC is useful in the case of crossover. In the PC will define how many number of children will be there with respect to population. It is a percentage. Suppose we have 100 number of population, then if there will be 0.9 PC, then there will be 5 children will be there. If it is the one, then total number, if it will be one, and we are using number of population 50, then 50 children will be there. Okay, and gamma is there, and it is this parameter is used in the crossover, and useful for it is used in the crossover, since we know that in the case of binary coded GA, it is this example is related to the we can say, this problem is a real number problem. It is not a binary problem. Here, in the case of binary coded GA, the crossover is very easily done. In that case, we just decide a crossover point. Maybe it may be a single crossover or double crossover, but in that case we just swap the values of parent 1 to parent 2 and parent 2 to parent 1. It is easily done. But in case of gamma is a parameter used during the crossover. I will tell you later that when it will be in the use. So mu is the mutation rate. As I already told that genetic algorithm generally consists of selection, crossover, and mutation. In mutation is nothing but it is the error in copying the in biological term. It is the error in copying the genes value. So mutation is nothing but we are going to alter randomly the value of the sum of the genes. So it will be helpful it will be helpful for exploring the search space randomly. In case of if your solution is trapped in the local minima, then mutation is very much helpful, since it will randomly alter some of the genes and get help to get out of the local minimum. Similarly, mu is the mutation rate. As I already told, right now it is a 0.1 it is 1%. After that, sigma is there. So sigma is there. So in generally, mutation rate is also get altered, and we use a Gaussian distribution function to alter the mutation rate. So for that purpose, we are using a mutation step size. in which the sigma value is going to change with the number of iterations. So these are the initialization parameter, hyperparameter, which are required for the genetic algorithm. After that, we are going to evaluate. After the initialization, we are going to evaluate the genetic algorithm by using this function, which has two input. One is problem structure, and other is a parameter perm structure. So and after that, we are going to show the results by the plot. Here we are using the semi-log. We can use a semi-log as well as we can use a normal plot. Semi-log is used for checking the convergence of any convergence of you can say semi-log graph is suitable when you want to find a minute changes in your plot. So I will later show that what will be the difference using the semi-log plot. So now we in a nutshell summarize this whole the GA process, but the main which is the GA algorithm is inside this GA.py file. So this is again we are doing importing necessary libraries, and after that what we are going to do, we are going to define the run GA.run function. So we have it has two input structures. So from structures we are going to extract the value necessary for this we can say we are going to import the necessary variable which are used in this G algorithm. So here we extracted the problem parameters, and similarly here we extracted the GA parameters. Now look at here. We use we use the NC term. Here we okay we PC into number of population. So here NC is the number of population for crossover. Crossover should be taken in the even mode. As we know that when we are going to mate different parents, so for different parents, so what will happen? There will be for every calculation, if we are going to number equal to number of proportionate children. Wait for here. Look at, so I will discuss when it will be used later. So gamma, as I told you, it is the parameter which help in exploring the search landscape, and when it will encounter, I will tell you that what will it tells. Similarly, mu and sigma are there. So what we are going to do that we are going to create a individual chromosome, or you can individual population in it in empty individual. They are every chromosome has every chromosome has its position and cost. Since we are initializing, so they are no values. After that we create a best solution and best cost. This is the global values. This is for the global optima. In case of genetic algorithm, there is no no personal best is there. Personal best is there, but that is not so we are going to define a structure. We are using deep copy in here, since we are using the same structure in here, but we don't want to alter the value of best solution as the individual value is going to alter. So we are using the deep copy in here. Okay, So after that, we are going to, since it is a minimization problem, so we have defined the maximum possible worst value as a best cost in the initialization, right? So this whole is empty is just initializing a single a single population. So here we are using the repeat function, empty dot repeat function, and we are generating a population population of size equal to number of population. So for I in the range of number of population, we are going to calculate. Uh, we initialize the position for each population or each chromosome. I'm going to evaluate its position, not evaluate. We are initializing using the uniform function from the random module, and its values are ranging from between variable minimum and variable maximum, and the size is equal to the dimension of the problem space or subspace, right? And after that, we are using evaluating its cost. So its cost will be cost function, and we are inputting its position value. After that, we are checking each individual population cost and compare it with the global best cost, and then we check the if the cost is if the global cost is the part is the if the population cost is less than the global cost, then we are going to update the value of best solution or the global best solution using this deep copy function. Okay. So after that, best cost. Okay. Okay. After that, we have initialized the best cost of every iteration. This is the best cost of each iteration. We initialize, and the size will be equal to the maximum number of iteration. So that this is for the purpose of storing all the best solution after each iteration. For sake of so after that, we run a main loop. In this loop we are starting iteration from 0 to means iteration 1 to number of maximum iteration using for loop, and we initialize a list for collecting all the children population. As I already told that initially in the first step we have the whole population is selected for the parenting purpose, but after that we are going to going after mating they are going to produce the children or offsprings. So after that, what we are going to, as I already told that each NC is the number of proportion number of children which are going to be generated. NC. Since I already told that for every in every step there will be two children from two parents. There will be two children. That's why we are ranging from NC by 2, not up to NC number of children. NC is there, and it should be rounding means it should be integer, so that since it can't be float. Okay. So first in the genetic algorithm, genetic algorithm, there are three steps. Selection is the first. So this is a selection region. So selection, as I already told, that selection is of multiple types or selection are there, but right now I'm using a random selection method. So in this what is going to happen, this code is going to generate a random array of size equal to number of iterations. It has it has a random values from just like 1 2 3 up to number of iteration, but they are not in the order. They are randomly these values are randomly in the random arrangement. So we are going to select the first two values, and suppose if it is 5 and 8, then the we are we are selecting two parents from f- at the position from 6th and 8th. For example, we can say that q0 is 0 and q0 is 6th and it's 8th. So two population from one is from two chromosome, one is at from 8th position and 7th position get selected. It is totally randomly right now. So after that we are doing crossover. So these two parents are selected. Now we are going for mating these two chromosome. So for that purpose, what we are going to do, we are going to write a function. We write a function that is called crossover function, and it will generate two childrens, C1 and C2. So the code for the crossover function is there. Let's explore this. What is going to happen? So this is a crossover function. So what is going to do? We have deep copy so that when we are going to change p1, its value is not going to be changed in c1. So we copied p1 into. Okay. So we are going. We have two children. We initialize two children, C1 and C2. It can be P1, no problem. No problem. We have C1 and C2. We just initialize. We create a C1 and C2, just like P1 and P2. And then, as I already told that in case of binary, in case okay, in case of binary crossover, we don't need this gamma value can be 0 and 0 and 1. We are defining a alpha function. So alpha function is going to generate a random vector, a random array of same size as size of the position equal to position size. We have a same. So what is going to happen if alpha minus alpha. In the case of binary coded GA, this alpha is working like a masking. But in here, this alpha is also like a masking. But this gamma is going to going to be added and going to okay. This we generate this alpha from this gamma, and this alpha is going to linearly combine these two p1 and p2 positions. There is a linear combination there is a linear combination for the purpose of crossover. So in case of C1, we use alpha alpha for P1 and 1 minus alpha for P2. Similarly, whereas in case of C2, we use position 2 multiplied with alpha, whereas so it is a crossover. This kind of crossover. 1 minus alpha is there. So in return, we got a two child, C1 and C2. So in C1 and C2 crossover, in case of binary GA, it is very much easy. But in case of real coded GA, these are going to be there will be a term that is gamma. This gamma term is added for the exploration purpose. So C1 and C2 are there. Now we get C1 C2 which are new childrens. So after that we are going to add a mutation in C1 and C2. So mutation is given by mu is there and sigma 2 two inputs are there, as well as there is a C1 that is cross that is a children one and children two. That are the children one and children two. So for mutation purpose, this function is used, mutation x mu and com sigma. Again, we used y in here. Uh, okay, uh, mu is used for flag purpose. Mu is there to generate a random to compare a random number generation with a mu. We will decide whether a particular whether a particular gene in the chromosome is going to be mutated or not. So for that purpose, if the random number value is less than mu, then less than mu, then we are going to mutate. In that case, we will using this line of code, we will find out that which indices are 1 and which indices are 0. For those indices which are 1, we are going to change the value of that gene in the chromosome. Otherwise the value is not going to be altered. So by position, as we already deep copied this x value into y, we change the position by using this mutation function. Sigma here is used to generate a random number. In case of binary coded genetic algorithm, it is very much easy to do the mutation. In that case, we can mutate only by using the complement. Means if we have 1010 are there in the chromosome, are generally there. So in that case, we just complement. One become 0 and 0 become the 1. But in case of real coded genetic algorithm, we have to add a we add a random terms in the real values. Since the value of the each gene in the chromosome are real valued, so we can't complement easily. So for that purpose, what we do, we add
Yes.
I'm audible. Any question?
Yes, you are audible. How much time will you take to wind up?
Okay, ma'am, I will complete within 5 minutes, ma'am. 5 to 10 minutes
After
max.
you, one more is there. One more.
Okay, ma'am.
I mean, resource person will explain.
Okay, ma'am.
Okay.
Okay, ma'am. I will complete. Okay. So what is going to happen in here in the case of binary coded genetic algorithm, it is very much easy to complement or to mutate each genes. But in case of a real coded genetic algorithm, we cannot complement. So for that, what we are going to do, we are going to add up a random terms in the each respective genes. So for that, we generate a random terms, but that random term is also taken from a Gaussian distribution, a random Gaussian distribution with a sigma square is its various value. So what is going to happen, the mutation is also going to change. It is also adaptive with the sigma value. As a sigma value, we are going to change, so it is also going to change the mutation rate. So after that, what is going to happen, let us complete fast. Okay. After mutation, we apply the bounds. Bounding means the similar. We are positioning or we are limiting our variables into the variable maximum and minimum values. After that, we evaluate the cost of the each children's, and we will check out if Okay, if the and then we will compare. We will compare the cost of the each both the children's with best cost. If the best cost is if the children cost is less than best cost, then we update the best cost. Then we append, means we collect the children's, two children's. Then we what is going to happen when we add both parents and children's merge. Okay, after that we have to again go into selection process. So what we are going to do, we are going to short the population of parents and children's using the cost values in the okay. After that we select the best valued cost function using this code offline. Then we update the best cost in the best cost iteration with iteration value. And then the print, this is the print for the iteration number, iteration best. After that we create again one structure. In that structure we are going to add the population, and then best solution, and lastly best cost, and output that structure is this structure will be the output of the that cost function. So let's run it. Let's run it for 10 dimension problem. Okay. Last region function. Wait for a minute. So this is the same rastrean function, and we are getting the best cost value 4.926. Whereas the global optima of for this function is at the origin, that should be a zero cost value. So I'm going to increase number of maximum iteration.
Chance pauna naik is in play. We are not last to get we are like
next year when you see women group we form civil code.
itu jamala aste.
Malam beli already nala MLA goes to an board like problem
Jamala bisyo lo. Untuk video kok na.
Currently tika treasure ka chauthi bana na unka pura
okay, this is a curve, and we are near the global optima. So this is all about the genetic algorithm. So in genetic algorithm, what we have done, we have used only random selection. But if I am going with roll table selection, then I guess the convergence will be faster. Okay, because random.
You just have to score certain marks,
Okay, so we can combine different possibility, different kind of techniques, and in such way we can explore a different possibility in genetic algorithm. So this is all about the genetic algorithm. I hope I should have to conclude since hello.
Yes.
Ma'am, should I have to conclude?
Yes, you can.
Okay, ma'am. Okay. So this is all about. I discussed two techniques. One is based on evolutionary based technique, and other is based on swarm based technique. I hope you get understand. If there is any query, please ask. I hope I will capable of answering the questions. Please, any question.
So questions from participants.
Okay, then
Okay, thank you, Rohit.
thank you, ma'am. Okay, ma'am.
Thank you. And you very nicely explained both the algorithms. And thank you from the team of Faculty Development Program of Nagaland University. Thank you.
Thank
Thank you so
thank
much.
thank you, ma'am. Okay.
And I would like to invite now Muthu Kumar, Dr. Muthu Kumar, to explain the remaining part of his hands-on. And the first part he had explained on 17th. And the little bit that day he couldn't complete because of his network problem. He wants to complete right now. So welcome Dr. Muthu Kumar, and you can start your presentation.
Hi, thank you. Thank you for welcoming Dr. Sujata ma'am. Hi, good evening all. We'll start with the thing like last session I was handling image processing, infrared image processing. Last session I was told you about once we finish the image processing of infrared images, and then we'll wanted to show the demo of activity detection of of a person using infrared images. So let's begin with that. I hope everyone saw my screen.
Yes, it is visible.
Yeah. So last time, this is what we discussed about how do we process the infrared image, and how do we enhance, and how do we smoothen, and then thresholding, segment, and then identify the edges, and about the analysis of the images. So, and also I shared the data set and the notebook file. I hope you guys received, and you must try it out. Now we're gonna see about how do we process the infrared image, and from there, like we try to identify the activity. So what we try to did is we try to collect the data using infrared, and also the RGB camera at the same time. It starts, both the device starts at the same time, so it will be synchronized. So so when we got the both the camera images and the infrared images, now we need to process the both. So this is the library we try to import it, and then these are the RGB images from the camera. Okay, and then we try to show the images like camera images. This is a camera image, and this is the coverage area which we try to covered using the infrared, because the infrared range is which is a very small coverage area, like which is 3 meter and 4 meters, 3 cross 4 meters. So this is the, but camera has a wide angle, so it can able to cover much more area. So I would like to show the infrared data sensor frame.pkl. This saves the infrared data has been saved from the sensors, and once you import the infrared infrared data using a pickle library. So the data is in a pickle format, so we need to use the pickle library that has been already been installed over here. Okay, so within the pandas has a pickle library, and so it can able to read the pickle file, and we try to list out the number of total images and the RGB images and the infrared cameras, and then we try to match with the corresponding frames, like for example, like we extract the heat to camera and camera to heat, like what it is, like camera images and the RGB images, and get the corresponding for the infrared images. It's already sent, but there will be a minute delay will be there, so we try to ignore the first 2 to 3 frames and last 2 to 3 frames, then we try to find the corresponding ones, and then we converted it into RGB images. And then we combine all the three together, because infrared sensor collects only the temperatures. So when we wanted to convert into RGB images, we need to create three different MPREs, and then we need to reshape that whole array into 24, 32 into three channels. That is nothing but like infrared resolution is 2432, and three channels is nothing but like RGB. And then we convert that into RGB images, and now we wanted to visualize the images. This is corresponding images of this. Yeah, sorry, this corresponding images of this images. This image corresponds to the this infrared image, because you can see this camera has a wide angle, so it can able to cover much more larger area, but the infrared has a very low resolution. It can able to cover only 3 cross 4 meters, so which is very less, so it can able to cover only these areas. So the camera has been fitted out in the ceiling, center of the ceiling. So now we extract the camera images and the infrared images. Now we try to uh, analyze the images through the various um, visualization, and then like once we analyzed, okay, so we try to find out the activity of the images next. So this is how we analyze both the RGB images and infrared images together. Okay, and then next we try to classify. Let me show you. Like yeah. So next we process the RGB and infrared images. Next we try to classify the activity of both using infrared and RGB images. So RGB images are try to use it for labeling the activity of infrared images. So as I said, like we try to import the sensor data, and then this is nothing but the annotations of the activity that has been annotated to the sensor data. So we create a separate CSV file, and each file represents each sensor data represents an activity that has been put it up in the CSV file. Like for example, first image activity is like walking, standing, like that. So total number of images and total number of frames has been extracted, 4778 and 4436. As I told you earlier, there will be a minute delay will be there, so we try to ignore starting some of the frames and ending some of the frames, and then the same thing we try to convert into RGB and all these things. So this is how the data frames looks. These are the temperatures of the infrared images. Okay, and these are the image file name, and these are the activities like walking. So this is the data we trying to classify. Okay, so we have like total like 5 classes, like standing, walking, falling, and sitting and standing. So total 5 classes will be there. So number 4, total 2076 images was there, and 1366 images was there, 602 images was there, 323 images was there, and 69 images. These are the classes. Total 5 classes we have. Like each classes have these number of images. Okay, and then we try to run through the neural network. So we need to split this. This is the whole data. This is we need to split it to the train data and test data. Using test size is 0.2. Okay, x train, x test, y train, y test, and we try to split this x and y to 0.2. That is nothing but 80% of training data, 20% of testing data. So random state is like for E2, randomly it takes data from the total data and split it into 80% and 20%. So now we're gonna create the neural network, which is nothing but CNN. CNN is used to classify the image data. So that gives the best result. So what we try to do is we try to build the CNN. These are the libraries we need to import, Keras, and TensorFlow and all these things. So Keras is a library, contains like Keras and TensorFlow contains Keras that contains all the layers, optimizers, models, and things. So you just need to import these packages to build a model. Once you import the images, once you import the libraries packages, so that you can directly call the layers and optimizers and all these things. So once you pre-processed the data already, then you need to tell which is x and y. X is nothing but the images, y is nothing but the activities, like whether it's walking or not walking. Like for 5 classes we see, right? 0 to 4, these are the 5 classes. That is nothing but it represents a y. Okay, so then we try to tell like y train, like, so usually here y train and y test is represents the total number of the classes. So that is what here we try to represent. Okay, and then next we need to give input to the CNN in the shape of 2432 by 3 channels. So this is the total number of images, 3548 images in the format of each image in the format of 2432 resolution, and 3 channels RGB. So X train is the training data, and this is a tested. X test is the testing data, and the total 5 classes which will be there, which we already told you, walking, standing, sitting, and all these things, falling, and all these things. So total, this is a X train and Y train will be used for test. Training the neural network, and X test and Y test has been used to validate the model. Okay, so now we're gonna build the model, like model equal to sequential model. Okay, and then you can try to call the layers, conventional 2D layers, which contains filters, 32 kernel size, which is 5 cross 5, and the padding is like same, like we are not doing the padding. And activation function we use a ReLU, and the input shape is 2432 cross 3. So this is nothing but each image resolution. So each image, when we give input, that will be in the format of 2432 3 channels. So 2 convolutional 2D layers followed by max pooling layers, and then 1 dropout. Okay, so this is kind of conventional block, we'll say, and then we try to use 2 conventional block, and after that we try to flatten is nothing but we try to make it in the single dimension vector, and then we use a dense layer, and after that we use a dropout, 0.5 dropout, and then final, this one is a output layer we use a softmax activation function. So total we have 5 classes to classify. So we use 5. Okay, and once you build the model, then we need to define the optimizer for it. So we use RMS proportion, learning rate is 0.001, and Riho is 0.9, and epsilon is learning rate
Aji lawa afternoon la
0.8,
session
and the decay is
ka part session kali katio
0.0. So this is the optimizer, we defined it, and afterwards you define, these are the hyperparameters. Once you define the optimizer, we need to compile the model, compile the CNN model we built. So we use loss function as categorical cross entropy loss function, and the metrics used to measure, which is accuracy, has been used to measure the performance of the model. And once you compile the model, now we need to fit the model. So we need to train and test the testing thing, which need to be done at the same time. So we used epochs, 40 epochs to run. Okay, so when we start running, so gradually it start with the loss 1.2, and the accuracy is training accuracy is 0.46, and validation accuracy is 0.59. Later it becomes like increase, and the training accuracy becomes 0.94, and the validation accuracy becomes 0.88. So once we train that, next we need to evaluate this model, how effectively it was being trained, and how the model, the performance of the model is. So we need to plot it through the confusion matrix, how it's correctly classified. These are the classes 0, 1, 2, 3, 4, 5, and we try to check the classification of each classes, and it's visualized in a way, and we use the metrics called accuracy. And this is we build a model using TensorFlow and Keras, like and also there is another package we can use, PyTorch, and based on that also you can build a model that will be some people are comfortable with PyTorch, some people are comfortable with TensorFlow. So we try to build model through the TensorFlow. So we try to reach an accuracy of this sample test data. We try to get 88, and for our validation test, and for training 94%. So this is how you build a model, and you evaluate the model using confusion matrix and the accuracy. So this is how we need to classify the activity. And I'll share you I already shared the data set of infrared infrared images, sensor dot frames in the previous files. I'll share you with this notebook. Please try with that data set with the classification. So it will be more helpful. That's it for today. Thank you.
I think it's over.
Thank you. Thank you, Dr. Kumar. Any question from participants?
Yes, I will share. I will share the notebook now with the same link. Any questions? Please.
Questions? Yeah, there is a question. What is the role of optimization?
Yeah, it try to optimize the model of like how effectively it is getting the model is trained, and try to find the activity which is probability nearly equal to adjust the weight and bias and make it to exact probability of the classes. There is a lot of optimizer which is there, like you can try, but we use RMS like proportions. There is stochastic gradient descent optimizer gives very good accuracy when we build actual model. This one I did it for hands-on training experience. So when we actually do on real data, so we use a stochastic gradient descent optimizer that help us to improve our accuracy. To yeah, there is a lot of optimizer which work based on different problems and different data sets. Okay. So anyone?
Someone wants data set, Santosh Sharma.
Yeah, I already shared the data sets in the previous link. It's
Yeah,
already
it was shared in the last session. I mean,
yeah.
17th.
Yeah, I'll share the notebook now. The data set is previously I shared already there.
Yeah, yeah. So no more question. Thank you, Dr. Muthukumar.
Thank you.
It was really a long day for us.
Understood.
We had 3 sessions and followed by hands-on by Dr. Professor Panda and his students, and then by Dr. Muthukumar. So I think all of you must be tired and you need some refreshment. So, and also I would like to thank my team, my students, and system administrator, and my faculty members who are working here. From morning, and today in Nagaland, our university has 2 days holiday. Like we used to have Saturday and Sunday, both days are holiday for us, but still they have come and they are working for making this program a successful one. So I thank all of them, and also thank all the participants for their patient hearing, and made this program a successful one. So again, I would like to see all of you tomorrow morning. Not exactly morning, we are starting the session. We'll be again starting the next 5th day session at around at 1 p.m. And the session will start by another eminent speaker, Professor Utpal Roy. He is a professor of Department of Computer and System Sciences, Vishwa Bharati Samtiniketan, West Bengal, and he will speak on keystroke dynamics and security issues in the modern IT world. I'm sure all of you will enjoy his lecture, and it's a nice one. So thank you all for joining this session.